Hello everyone. So today I am here for a presentation on distributed systems, and I hope I will make it clear to the beginners that what is a distributed system and how it works. So let's proceed. What is a distributed system? A distributed system is basically a group of computers working together to achieve a common goal. So how does it work? So instead of buying a supercomputer, you are buying 1000 normal computers and you are combining their power, which actually turns up into more than a supercomputer actually. So before going into detail, we would learn to know another topic, which is vertical scaling versus horizontal scaling, because this is really important before going into distributed systems. So by vertical scaling, we mean to upgrade a computer's existing computing power. So let's say you have a computer which has 8 GB RAM and 1 terabytes of hard disk. And what you do, you are replacing the 8 GB RAM with 16 GB or 32 GB or even 64 gigabytes of RAM. Maybe you are replacing its hard disk with from 1 terabyte to 2 terabyte. So you are essentially trying to convert the existing computer into a better computer. But what happens when you need this level of computing power, which is actually not available in the market? Let's say you cannot just go in the market and buy 200 gigabytes of RAM. So where vertical scaling seems impossible, actually horizontal scaling comes to the rescue. So horizontal scaling lets you scale out your computing power to nearly infinity, which you can't even imagine with vertical scaling. So how this works? Instead of increasing the computing power of one machine, we are buying different machines with the same computing power. So if I have 100 computer and each of these computer have 8 GB RAM, 8 GB RAM, 8 GB RAM, so eventually I end up into 800 gigabytes of RAM, which can't be imagined with vertical scaling. So this is really an interesting concept. So why are we learning this for learning distributed system? Because distributed systems are actually in real world horizontal scale systems. So I think I'm clear up to now. Let's move forward. So what do we normally see in a typical small business? Fewer customers, a web application hosted somewhere in the web, a single database server deployed with periodic backup mechanism. So why do we need periodic backup? Because let's say the database got deleted somehow or crashed or deleted or destroyed. The periodic backup actually helps us to retrieve our customer data up to a certain extent. For example, if we have a backup policy every 30 days or every 15 days or every 7 days, we can actually retrieve all of our data if the database got deleted up to that, up to the last backup taken. So what is the problem when a business grows? That let's say the customer base has evolved from 100 to 1000 to 10,000 to millions. So what happens is eventually the single API server which is deployed here becomes unable to take the huge amount of load sent by all of the customers. So what happens is the API starts crashing and this can't bear any more load. Like it can't take thousands of user requests at the same time. So what normally we have to do in this scenario is we scale out. So how do we scale out? As we have seen before, horizontal scaling. So let's see it in the next slide. So we can see that we have horizontally scaled one single API server into multiple API servers. So we are not eventually increasing the RAM, increasing the CPU computing power of the API server. Rather, we have multiplied the number of API servers so that now all of them can combinedly take the workload distributedly and they can serve the customer seamlessly in a very few amount of time. And what does the load balancer does? Whenever a user hits the browser from, let's say, Google Chrome or any other web browser, the user doesn't even know that how many web servers are there. The load balancer eventually decides that which of the servers are busy and which of the servers are less busy. So it is the duty of the load balancer is to distribute the workload to the less busier server. So this is how horizontal scaling actually helps us to deploy multiple API instances and serve the workload with the help of a load balancer. But did you think of a question which may arise at a certain point? Let's go to the next slide. Wait, we didn't scale our database. I have deployed 10 API instances, which because one single instance was failing to take the load. But what if the single database server cannot take the load? We didn't scale that. So yeah, it is a good question. So let's recall our previous slide. We can see here that we have multiplied one API server into 4, or even it can be 10 or hundreds. But we haven't multiplied the number of database servers. What if the number of requests are so much at single unit of time that this single database server is crashing? This single database server has not that computing power to serve all these requests in the same amount of time. So what happens then is, even after putting a load balancer and multiple number of API instances, still the application crashes. The application doesn't get any proper response. It is crashing. It is not responding. So what happens then? So the next thing is distributed system. So the answer to the previous question, what we have left is we must go into distributed database system. When the architecture is not enough just to scale out the API servers, we also need to essentially scale out the database servers. Because think of tech giant companies like Google, Facebook, Amazon. They have billion users using their application all over the globe. And if they have a single database server, can the single database server really take the load? I think no, it is not possible. So all of the tech giants are eventually following distributed database system, where they have multiple number of database servers which are combinedly together serving the users, because it is not possible in a single computer. So I think I am little clear up to this point what a distributed database system is. Now let's go to the next slide. Challenges of a distributed database system. So what are the challenges? As we have multiplied our databases from one to many, of course there are challenges. Many people say distributed systems are super duper complex. They are so complex and you cannot just do it easily. So the distributed system database, so the challenges of a distributed database system are classified into 3: consistency, availability, partition tolerance. So there is a very popular theorem called CAP theorem. So if you study the CAP theorem, you will see that how CAP theorem explains each of these concepts and how they are so related to a distributed database system. So let's go to the next slide. So at first we look into C for consistency. So what is consistency in CAP theorem? Let's say we have multiplied the database into multiple databases so that multiple databases can combinedly serve our users, as we have discussed before. So what happens, let's say we are working with a ticket booking system and a ticket is sold, and this database is showing that the currently available tickets are 0, and this database is telling the available tickets are 1, and this database is telling the available tickets are 1. So this is a total inconsistency. We must ensure that whenever tickets get sold, all of the databases should have the latest sync of data. Like all of the databases should know that no tickets are left now. Because if somehow this database means that one last ticket was sold, there will be total inconsistency. Maybe multiple customers will be paying for the same ticket and your system is in a mess. So the challenges for consistency is all database must share consistency in data. The higher the consistency, the better the system. For example, if you look at the cloud databases like Azure, AWS databases, what they provide, you will see they are telling that our database is 99.98% consistent, or we provide 99.9999% consistency. But you will never see anyone say, any cloud database provider telling that, yeah, our database is 100% consistent, because this is practically impossible. Why? Because let's say a ticket is sold, and that ticket is sold through this database interaction, and this database alone knows there are 0 tickets available, but these databases yet don't know. So there must be a communication, there must be a network channel between the internal databases, which essentially updates these databases too about the update. So no matter how fast network connection is established, it cannot be 0 second, it can be milliseconds. With very high technology, you can reduce the millisecond into microsecond, nanosecond, but you cannot just take down to 0. That is the reason that since you cannot reduce or completely take down the difference of data consistency maintaining to zero, no single practical database on earth can guarantee we are providing 100% consistency. So yeah, you will always see these type of keywords, that 99% or 98%. Okay, so let's go to the next slide. A for availability. So in CAP theorem, there is a term availability. What does it mean? Availability means in a distributed database, anything can go wrong. A network node may fail, a server may fail, a server may crash, a network may become unavailable due to some unexpected error. So the availability stands for each read and write request will either be processed successfully or receive a message that the operation cannot be completed. Like, which means that whenever a user hits into a database through an API, the database must return a successful response, or the database must respond that uh, the operation cannot be completed. But we are not expecting connection timeout. We are not expecting that API isn't responding totally anything, or a database isn't responding anything. So that is the concept for availability. Then we go to the next slide, which is partition tolerance. In the CAP theorem, the last term, partition tolerance. Partition tolerance says the system should continue operating even if the network connecting the nodes has a fault. For example, let's say we have a distributed system and we have 10 databases which are serving our global users. And what if some of the network connecting the databases fail? Should the whole system go down? Should the half of the system say that there is an internal server error? Or the system should be that much intelligent that even if one part of the network is failing, the rest of the system continues to work seamlessly and the customers are getting this proper responses instead of telling database unavailable. So this is what partition system says. Partition tolerance says the system continues to function and uphold its consistency in spite of network partitions. So these are little confusing terms to me too. I don't even properly understand some of these differences between availability, partition tolerance. So if you are really interested in knowing more and more about these topics, I would recommend you study more. You can go for the book Grokking the System Design by Design Gurus. Okay, so let's go to the next slide. So this slide eventually says a distributed system cannot guarantee CAP altogether. Like we have said before that a distributed system has three laws in CAP theorem: consistency, availability, partition tolerance. But it is till today, it is impossible to design a single system which can guarantee the best of consistency, availability, and partition tolerance. There are so many discussions on it, so many theories you can read more and study. It says that no system can guarantee all of these. Like you have to either sacrifice availability or consistency or partition tolerance. So if we look at in the most of the relational databases in today's world, they are more of CA. They are fulfilling consistency and availability to a very high level, but they are not fulfilling partition tolerance to that level of high level. So you can see that RDBMS is in between availability and consistency. So if you are working with relational databases like SQL Server, PostgreSQL, or you can say MySQL, you are likely to accept the fact that your database is better at consistency and availability, but not partition tolerance. And now, if you are working on non-relational databases, like maybe you are working with MongoDB, maybe you are working with Redis or other non-relational databases, you are likely to provide better consistency and partition tolerance to your customers. You can see that MongoDB sits in between consistency and partition tolerance. So you have to either sacrifice availability if you are using MongoDB, or you have to either sacrifice partition tolerance if you are using a relational database like SQL. Again, they are telling that databases like Cassandra, CouchDB, they are more likely to offer you a better availability, better partition tolerance, but not better consistency. So this is a challenge. You can study more on it, and based on your scenario, based on your business idea, you have to decide that Do your business require more availability, or do your business require more partition tolerance? Then you can come to a conclusion to decide that should I go with MongoDB or Redis like non-relational databases, or should I go with relational databases like SQL, MySQL, PostgreSQL. So this is all about it. I have even less knowledge about these topics. These are still some buzzwords to me, like availability, partition tolerance. Sometimes I mix up one theory to another, but still, for today's presentation, I think this was it. We can go to the next slide, which is, yeah, thank you. And if you have any idea, or if you have any suggestions for me, how should I improve, or on what more content should I make more videos on, you can, of course, suggest me, or if you have any advice, you can, of course, share me. Thank you all. Bye-bye.